Welcome back, everyone. Industrial manufacturing now shapes materials using concentrated laser energy without physical contact. Across sectors such as automotive production, electronics assembly, aerospace fabrication, and medical device manufacturing, lasers function as primary production instruments rather than niche additions. These systems deliver controlled energy to specific locations on a workpiece. The delivered energy performs cutting and welding, as well as surface modification. Industrial laser systems are currently operational in many factories and are no longer limited to experimental settings. Factories now demand tighter dimensional tolerances and faster line reconfiguration between product variants. Unlike traditional tools, laser systems do not require direct contact with materials. The absence of physical contact changes how machines are positioned and how process layouts are arranged. Maintenance practices also shift, reshaping how modern production lines are managed at scale. Multiple industrial laser system types operate continuously at industrial scale within modern production facilities. Fiber laser systems run for metal cutting and welding in high-volume environments. Solid-state and high-power laser systems operate in precision marking and surface treatment tasks. Supporting components such as optical assemblies and motion platforms integrate directly into factory automation. Many production facilities now design workflows around industrial laser systems from the beginning. This approach differs from earlier practices, where lasers were added after mechanical processes were defined. The move toward lasers depends on how industrial laser systems determine achievable precision. The same industrial laser systems also determine achievable production speed in current manufacturing environments. Electronic regulation of laser energy maintains dimensional accuracy during material processing. Mechanical tools rely on physical edges that wear down as they contact material. Wear steadily alters cut geometry and dimensional accuracy over time. Laser systems avoid this limitation because energy delivery is regulated electronically rather than through direct contact. At the processing point, beam shape and intensity remain stable when optical alignment and power regulation are maintained. Beam stability allows manufacturers to hold tight tolerances without repeated recalibration. In high-volume production, consistent precision reduces scrap rates. Consistent precision also lowers inspection effort. Laser systems are also used for surface hardening and fine welding tasks where uniform results are difficult to achieve mechanically. These conditions allow production lines to operate for longer intervals without stopping for tool replacement or recalibration. Laser beams change direction and focal distance without mechanical tool changes during operation. Mechanical cutting and drilling processes often require tool repositioning and pressure adjustments to manage heat buildup. Laser systems change beam direction and adjust focus parameters to move rapidly between tasks without stopping the production line. In automated environments, rapid laser beam switching shortens cycle times by eliminating mechanical delays. Rapid laser beam switching also improves coordination with robotic handling systems. Lasers trace complex cutting paths without tool changes, which reduces downtime between product variants. Industries with frequently updated designs rely on this behavior to maintain output without repeated mechanical setup. Speed here refers not only to cutting rates but also to how quickly the production system responds to new configurations. Non-contact laser processing eliminates several common mechanical failure points from production equipment. Traditional machine tools rely on bearings and gears that require lubrication and periodic replacement. Over time, mechanical components build up wear and introduce failure points. Industrial laser systems reduce mechanical complexity by removing direct contact between the tool and the material. Optical components still need maintenance, but their wear patterns are predictable and much easier to manage. Scheduled servicing can align with regular inspection cycles rather than emergency repairs. In facilities running continuously, fewer unplanned stoppages increase the number of hours machines remain in production. Laser systems also generate less vibration than mechanical tools, which reduces stress on supporting structures and alignment systems. Delivered laser energy remains confined to a defined processing zone during operation. Mechanical processes lose energy through friction and deformation beyond the target area. Laser systems concentrate energy at the processing point, which confines heat to a defined zone around the beam. Thermal confinement limits thermal impact on surrounding material. Localized heating reduces distortion and preserves material properties outside the processing zone. In welding applications, controlled energy input stabilizes joint formation, while in cutting operations, clean edges reduce the need for secondary finishing steps. Energy efficiency here refers to effective use rather than total consumption. These conditions produce consistent edge geometry and uniform weld joints, using less excess input energy. Digital control systems govern laser beam motion and operating parameters in real time. Modern manufacturing depends on close coordination between design data and physical execution. Laser systems receive digital instructions directly from design models, and these instructions control both beam motion and parameter settings in real time. Motion control systems also synchronize beam movement with robotic arms and conveyors. Digital coordination supports automated inspection during operation. When deviations occur, digital coordination enables immediate parameter adjustment without stopping the production line. Corrections are applied without stopping the line, which preserves continuous output. These linked systems replace manual adjustment with automatic response across machines, and digital alignment allows factories to maintain consistent output across multiple production sites. Industrial laser platforms operate continuously under demanding factory conditions. Trumpf, based in Stuttgart, engineers industrial laser platforms that are designed for continuous industrial use in factory environments. These systems deliver controlled energy for cutting, welding, and surface processing tasks across many industries. The equipment is built to integrate seamlessly into automated production lines, where stability and uptime are critical. By maintaining beam quality, power regulation, and serviceability, Trumpf systems meet the requirements of large-scale manufacturing. Their widespread deployment in operational factories shows that laser-based tools are now core production assets rather than experimental technologies. Fiber laser architectures deliver stable output through compact industrial systems. IPG Photonics, Oxford, has advanced fiber laser technology that delivers stable output with compact system designs. Fiber lasers are widely used because these systems combine high efficiency with flexible beam delivery. These traits make fiber laser systems suitable for cutting and welding applications where space is limited and energy management matters. This system architecture supports reliable operation over long periods, which is important in manufacturing. Maintenance demands are kept limited, allowing production to continue with minimal interruption. As fiber lasers increase in both power and adaptability, these systems are steadily replacing mechanical tools in tasks that once required several specialized machines. This progression reinforces the shift toward laser-centered manufacturing systems. Controlled laser energy enables precision joining and marking operations in modern manufacturing. Coherent Santa Clara develops laser sources and optical components for precision industrial applications. These systems deliver controlled energy for fine welding and marking tasks, where accuracy and repeatability are critical. Optical stability and beam control define how these applications perform. By refining energy delivery and beam consistency, coherent systems allow manufacturers to achieve uniform results across entire production runs. These capabilities are especially important for industries that demand tight tolerances and dependable output. Lifecycle cost analysis measures how manufacturing tools operate and age over time. The ETH Zurich Institute for Manufacturing studies manufacturing system efficiency and provides analysis related to lifecycle cost evaluation. Their research examines how advanced tools influence productivity and the total cost of ownership. These studies help inform decisions about adopting laser-based systems over mechanical alternatives. By evaluating performance across entire equipment life cycles, the Institute identifies which systems deliver lower operating cost per unit produced. This work shows that laser systems can reduce replacement, calibration, and downtime expenses compared with mechanical tools. Research activity continues around the integration of laser systems into automated manufacturing. Politecnico di Milano conducts research on advanced manufacturing systems that informs future laser integration. The work at Politecnico di Milano focuses on process optimization and automation compatibility. Research findings will support gradual improvement rather than disruptive change. Monitoring methods under development will provide clearer insight into process consistency and component wear. These efforts build on existing operational laser systems rather than replacing them. As capabilities improve, the range of applications suitable for laser manufacturing will continue to expand. Laser-based processing enables direct access to microscale features and internal geometries. Microscale features can be produced reliably without tool breakage. Complex internal geometries can be accessed through controlled beam paths. Surface textures can be modified to improve adhesion or wear characteristics. These capabilities expand available design options. They also allow engineers to optimize components for performance rather than ease of manufacturing alone. Product development cycles shorten as iteration becomes faster and more direct. Manufacturing constraints relax and open room for broader experimentation and quicker refinement. Compact industrial laser systems now operate outside large centralized factories. Smaller facilities and specialized workshops are implementing these compact laser systems tailored to specific tasks. This distribution broadens the manufacturing base capable of producing high-precision components. Supply chains become more resilient as production capacity spreads across more sites. Standardized laser platforms simplify collaboration between suppliers and integrators. As adoption grows, technical skills, spare parts, and compatible tooling are spreading across more locations. This distribution improves continuity when individual facilities experience disruption. Laser capabilities align directly with the operating requirements of modern production systems. Precision and reliability define competitiveness in advanced manufacturing. Laser systems meet these requirements more effectively than traditional mechanical tools across many applications. The adoption of laser systems reflects a structural evolution in how factories operate and how products are made. As this transition continues, lasers are moving from supporting roles to central positions within production lines. Manufacturing tools are increasingly defined by the controlled delivery of energy rather than physical contact. Tools are defined by the ability to deliver controlled energy with accuracy and repeatability. This perspective reshapes how engineers approach process design and optimization. As light replaces contact in more operations, factories experience lower vibration, reduced tool wear, and simpler maintenance routines. These manufacturing changes persist across equipment life cycles and alter how factories are designed. Industrial lasers are not a temporary trend. Industrial lasers are foundational elements of modern manufacturing infrastructure. Thank you very much for watching. Please like and subscribe.